Hello everyone, welcome to this video on the fourth elementary flow that we will be looking at, which is called the Vortex Flow. Just to recap, in the previous videos we have looked at elementary flows such as uniform flow, sink and source flow, doublet flow, and then we put together uniform flow and a doublet flow to get flow over a non-lifting cylinder. And in this lecture we will see another elementary flow which is called the vortex flow. So what is a vortex flow? So before I get into the math, let me just draw the streamlines of a vortex flow. So vortex flow has circular streamlines with the fluid traveling in concentric circles as I have drawn on the board. So clearly, if I use a polar coordinate system, the velocity can be decomposed into a radial component and a theta component. So from this figure, it's evident that the flow does not have a radial component because the flow is happening in the theta direction. So at no point there is a component of velocity in the radial direction. So this is the radial direction and that's the theta direction. So as you can see clearly, there is no flow happening in the radial direction. So VR is always going to be 0. Now let's look at V theta. We say that V theta is only a function of R, which means that a streamline which is at a given distance R from the origin is going to have a constant magnitude for V theta. As the R changes, the V theta is going to change. So compared to this streamline is going to have a different velocity in the theta direction, and that is a function of R. So we now assert that V theta is some constant divided by R, right? So you can check if this velocity field satisfies the continuity equation, which is the divergence of velocity being 0. So that's a simple exercise that can be done. So here at this point, let's try to find out what this constant C is. So for that we resort to a concept called the circulation. Circulation, which is typically denoted by gamma, is given as minus of integral V dot dl. So this circle here says that the integral is a line integral, and it is a line integral over a closed loop. So the line integral over a closed loop of V dot dl gives the circulation, right? So in this case, let's say that the circulation is gamma, and let's find out what the circulation would be for any given streamline in the vortex flow. So let's take that be the origin, and let me take a closed curve which is a circle of radius r centered at the origin. So now if I perform this operation along this loop, what would I get? So first of all, along this curve, V theta we know is C by R. So I have gamma is equal to minus integral v dot dl, right? So v is nothing but vr er cap plus v theta e theta cap, and since vr is 0, we have only v theta e theta cap, which is c by r e theta cap, right? So that is the v vector dot dl. dl is the elemental length along the curve that we are integrating. So in this case, the curve being the circle, so if I take an elemental length dl, this dl can be written as dl vector can be written as r d theta e theta cap, right? R d theta being the magnitude and e theta cap being the direction. So we plug in the value of dl in this integral, so that gives us r d theta e theta cap. So e theta cap dot e theta cap is going to give us 1. Therefore, before I do that, it's important that I put the limits. So this curve is a closed curve, and therefore theta varies from 0 to 2 pi, right? So now let me solve this integral. So c is a constant, it comes out of the integral, and the r here and the r there gets cancelled, and therefore e theta dot e theta is again, as I said, 1, and therefore what I get is an integral 0 to 2 pi of d theta, which is minus 2 pi c, and therefore c is minus gamma by 2 pi, right? So the velocity in the theta direction v theta, which is c by r, is going to be minus gamma by 2 pi r, right? So let me just erase the board and retain the result. So we have v theta is equal to minus gamma by 2 pi r, and vr is 0. So at this point, I would like to mention that the vortex flow satisfies the continuity equation throughout the flow field, and it is irrotational everywhere in the flow field except at this point, which is the origin. So I won't go about proving these two things, but you can physically understand this, because as you can see, there is no flow that is emerging out of nowhere, like in the case of sink or source flow, and therefore mass conservation is maintained in this case as compared to the sink or source flow, and therefore we can say that the continuity equation is satisfied. Now, to show that at the origin the flow is irrotational, one might have to take a mathematical approach which involves limits. So I will leave that as an exercise, but before I do that, I'll give a lead to how this can be done. So as we saw earlier, circulation is given as minus integral v dot dl, right? And in mathematics we have a well-known theorem which is called the Stokes Theorem, which connects a line integral to a surface integral. So this will actually be equal to minus integral over the enclosed surface. This is an area integral of del cross v ds, right? So this now del cross v is the curl of velocity, which is the measure of rotationality. And if you take the limit of the radius going to 0 and observe what happens to this quantity, you will realize that the curl will not be 0 at the origin, and therefore the vortex flow is irrotational everywhere except the origin. Now let's move on. Having found the velocity vector as shown here, we can now conveniently estimate the expressions for the velocity potential and the stream function. So first let's look at the velocity potential. So the velocity potential Vr is connected to the velocities as Vr is equal to dou phi by dou r, and V theta is 1 by r dou phi by dou theta, right? So let's look at one equation at a time. So as we know, Vr is 0, so dou phi by dou r is 0, and hence phi has to be a function of theta. Now let's differentiate this phi with respect to theta. So we get dou phi by dou theta is f prime of theta, where prime indicates differentiation with respect to theta, right? So now we plug this into this equation, that is V theta is equal to 1 by r f prime of theta, and therefore f prime of theta is r into V theta. Now we know what V theta is, which is minus gamma by 2 pi r. So this is going to give me into minus gamma by 2 pi r. The r and r get cancelled, which leaves us with minus gamma by 2 pi. Now on integrating this equation, we would get f of theta is minus gamma by 2 pi into theta. So that is what we get for f of theta, which is what we need. Phi is f of theta, right? So therefore, let me just erase all of this. So therefore, the potential function is minus gamma by 2 pi into theta. So one can do a similar exercise for finding the stream function for this specific flow field. So one can just use the formulae. Vr is dou psi 1 by r dou psi by dou theta, and V theta is minus dou psi by dou r. So I won't be performing the integration, but I request the readers to the viewers to try it out themselves, and what you would get is the stream function is equal to gamma by 2 pi logarithm r. So this is what you would get on integrating, right? So this is pretty much what a vortex flow is about, and we would be looking at how a vortex flow helps in generating lift. So in the subsequent lecture, which I'll be posting shortly, we will be looking at how a vortex flow can be added to a non-lifting flow over a circular cylinder in order to make it a lifting flow. So I hope the content of this video was clear. If you have any doubts or questions, you can feel free to post in the comments below. And if you have any feedback, please feel free to share them with me. Thank you. See you soon.